Welcome to Daily Papers, the podcast where we break down fascinating new research papers into something you can enjoy on your coffee break.
Today, we're talking about computer chips. They're in everything, from your phone to your car, but designing these tiny, complex brains is an incredibly slow and difficult process, taking teams of engineers months or even years.
But what if you could automate it? What if you could just tell an AI, hey, I need a chip that does this, and it would design the whole thing for you? Well, a new paper from researchers at the American University in Cairo might be a huge step in that direction.
The paper is called ASIC-Agent, an autonomous multi-agent system for ASIC design with benchmark evaluation. That's a mouthful, so let's break it down. First up, what is an ASIC?
ASIC stands for Application-Specific Integrated Circuit. Think of it like this. The main processor in your computer is a generalist. It's like a Swiss Army knife that can do a bit of everything. An ASIC is a specialist. It's a chip designed to do one single task extremely well and efficiently. Your phone has ASICs for processing camera images, your car has them for managing the engine, and so on.
And designing these specialist chips is a massive undertaking. First, engineers have to write a detailed blueprint, kind of like architectural plans for a building, but in a special hardware programming language. This is called RTL design.
Then comes verification. You have to test that blueprint relentlessly to make sure there are absolutely no bugs. You can't just release a software patch for a physical chip once it's been manufactured. If you get it wrong, you've just created a million very expensive silicon coasters.
And finally, you have to turn that verified blueprint into a physical layout, a literal map of millions or billions of transistors and wires. This stage is often called hardening. The whole process is incredibly labor-intensive and prone to human error.
Now, you might be thinking, can't we just use a large language model, or LLM, like the ones that power ChatGPT, to do this? They're great at writing code, right? And people have tried. But LLMs have some big limitations.
Exactly. An LLM is like a brilliant programmer who's sitting in a dark room with no computer. It can write code, but it can't actually run the code to see if it works. It can't debug in real time, and it doesn't have a long-term memory to manage a complex, multi-file project.
This is where ASIC-Agent comes in. The researchers realized that designing a chip isn't a job for one single AI. It's a job for a whole team of them.
So they built a multi-agent system. It's an AI super team where each member has a specific job. First, you have the main agent. Think of it as the lead architect. It takes the user's request, written in plain English, and writes the initial chip blueprint, the RTL code.
Next up is the verification agent, who is basically the quality assurance inspector. Its job is to create a rigorous testing environment and put the architect's blueprint through its paces. It simulates the chip's behavior to hunt down any flaws in the logic.
Once the design passes all the tests, it's handed off to the hardening agent. This is the engineer who takes the blueprint and turns it into a manufacturable physical layout. It uses a whole suite of open-source tools to place and route all the tiny components.
And there's even a fourth agent, the integration agent, which specializes in taking the finished design and making sure it can be correctly plugged into a larger standard chip framework. So you've got this whole assembly line of AI experts working together.
And to make all this work, the researchers gave this AI team two critical things. First, a sandbox. This is a safe virtual environment that comes preloaded with all the real software tools that human engineers use. This allows the agents to not just write code, but to compile it, test it, and build the design, getting real feedback at every step.
Second, they gave the team a super-powered external brain. It's a special kind of database called a vector database, filled with technical manuals, API documentation, and even curated insights from online forums where human engineers have solved similar problems. So if an agent gets stuck, it can query this knowledge base to find a solution.
Okay, so you've built this amazing AI team. How do you know if it's actually any good? The researchers found that existing tests were way too simple. They were like judging a chef by only asking them to chop an onion instead of cooking a full 3-course meal.
So they built their own test called ASIC-Agent Bench. This benchmark doesn't just ask the AI to write one little piece of code. It gives the system complex, open-ended, real-world tasks like designing a processor core or a memory controller, and evaluates it on the entire process, from the initial idea all the way to the final physical layout.
And to grade the results, they used another LLM as an impartial judge. This AI judge checks the agent's work against a set of key milestones, awarding partial credit along the way. It's a much more flexible and realistic way to measure performance on such a complex task.
So, the million-dollar question, did it work? The answer is a resounding yes. They tested the ASIC-Agent system using a few different powerful LLMs as the brains for the agents, including models from Google, OpenAI, and Anthropic.
The best performer was the agent powered by Claude 3 Sonnet. It successfully automated a wide range of chip design tasks, achieving an impressive average score of 88% on the benchmark. It particularly excelled at the most difficult tasks, outperforming its rivals significantly.
What's really cool is watching how it worked. The paper shows logs where the agent would try to build the chip, run into an error, analyze the error message, think about the problem, and then decide on a fix. It would then try again, sometimes failing multiple times, but iteratively debugging and refining its approach until it succeeded. It was behaving just like a human engineer.
Of course, it wasn't perfect, and different AI models had different strengths. The Claude-powered agent was the smartest, but also the most expensive to run. The agent using GPT 4.1 was the most cost-effective, but had the lowest success rate.
But the big takeaway here is that this multi-agent approach seems to be the key. By breaking down the monumental task of designing a chip into specialized roles and giving the AI agents the tools and knowledge to do their jobs, we can overcome the limitations of a single standalone LLM.
This could be a huge deal. Automating even parts of this process could dramatically accelerate the pace of hardware innovation. It could mean faster, more efficient, and cheaper development of the specialized chips that will power the next generation of technology. And that's a very exciting prospect.
That's all we have time for today.
Join us next time on Daily Papers, where we'll be digging into another new study. Thanks for listening.